Thank you, Robin, for agreeing to give your presentation to us. And with that, I will turn it over to you. So thank you very much.
Thank you so much, Roger. Pleasure to be here, and hopefully people can hear me okay. Yeah, I am unusual. There's no S, so there's only 2,000 Jenkin in the United States. There's something like 200,000 Jenkins the last time I looked at this, so that's why I'm unusual in that sense. I'm very lucky. I've played around with imaging ever since I got my first degree and have managed to stay in that. So I feel incredibly lucky to find imaging as a career just as it starts to take off as a uh, just as digital imaging took off and using images and cameras for information sources. So it's been very kind to me, and it's wonderful to be here at NVIDIA modeling imaging systems primarily to be used in automotive systems and some robotics and medical as well. So very lucky to do what I do and to work with incredible people such as yourselves and be a part of IS&T as well. Before we start the talk on using programmable light sources to simulate CFAs, I want to mention Uwe Artman at Image Engineering. It's really his company and his hardware that have facilitated this work. And really a big shout out to them who have donated the time on the equipment for nothing to enable this. So there we go. So what's our motivation to look at CFAs? So CFAs, color filter arrays, filter light onto the imaging sensor and provide us our color planes before demosaic. And to be able to do that, we layer filters on top of each pixel, and they usually have some sort of spectral response. Here I've made some CFA curves up, red, green, blue, cyan, magenta, yellow, and also put a clear there. And we can say create a green channel by filtering out anything but the green light, and it roughly looks like that. But one of the troubles is when we do this to create our color in our systems, we're really losing around about half of the light because we're filtering out everything from here that we could collect. We're just collecting this, so we reduce the amount of light by about half, which reduces the sensitivity of our system. So really, when we're talking about CFAs, we're talking about how to balance the filtering of light to get some sort of color signal against capturing as much light as possible to get as much sensitivity in our system as possible. And of course, that's important for automotive systems because we want to be able to have our cars drive us at night, and we're just relying on headlamps to illuminate the system. And with an inverse square law fall off for our headlamps, very rapidly we lose range, and then that limits the highest speed at which we can travel. And maybe folks have heard of FMVSS 127, which is a recent rule to look at the way cars behave for, say, pedestrian detection and things like that, and can stop. So we're trying to balance this filtering to get color signals against capturing as much light as possible. These CFA curves that I've made here are based on Fujifilm materials. They don't relate to any sensor, so I'm not sharing any information I shouldn't be sharing about other people's QE curves. So what are some of the practical differences between these QE curves? So I've got two similar pixels here. The only difference is the CFA. And so on the left-hand side, you can see a red, green, blue CFA set. And on the right-hand side, you see a red, yellow, cyan uh, CFA set. And they both have the same exposure time. And on the left-hand side, you can see even after CCM, you can see there's better color separation between the red and the yellow traffic lights. So color separation is one thing that we're concerned about. You can see less well color separation on the right-hand side. You can see more chroma noise on the right-hand side than on the left-hand side. But also, if you look in this area here, the home on the RGB is barely visible, whereas it's slightly more visible on the RYCY. So the Y and the cyan are slightly more transparent. So that's why we get this slight increase in sensitivity, but there's strongest CFA, CCM terms that are um, required to color correct this, so that's why we see slightly more color noise there. And I'll get to some of that in a bit. So I'm going to just describe some work that I did for a paper in 2021 when I first looked at this. The paper is open source. You should be able to download it from the QR code and the link there. That goes into detail about the simulations, and I'm not going to go into detail, too much detail here, because that would bore you to death, and we don't want to do that. So download it there, and you can get some of the finer detail on this. So the experimental flow chart for the simulation really starts off looking at illumination, surface reflectance, lens parameters, and some windshield parameters, sensor parameters in terms of the QE curves, and exposure parameters. And we have a noise model to estimate noise at an image plane for a given exposure. And we can also estimate photons at the image plane. We generate a raw flat field per channel. And I'm also generating some other images that I use for other things. We flatten both of these to Bayer images using the QE curves that we specify. We white balance, we demosaic, we apply a CCM, and then we can estimate from the raw. We can estimate a lot of pre-CCM, SNR, and dynamic range and other metrics. We can also generate a CCM, and I use a white point preserve in least squares method to do that, because it's deterministic and fair, I think, is the way I would put it, and white balance gains. We then apply those, and we can generate flat fields from which we can estimate more metrics, like the post-CCM, SNR, and dynamic range. We can estimate noise power spectrum as well. I also generate a sloping edge, so I can calculate noise equivalent quanta at the image plane, and MTF at the image plane as well. This simulation was used for some other work, looking at using dead leaves actually to estimate NEQ. We can convert into LAB and also look at color separation, which I'll talk about a little bit later as well. The details of this are in that paper that I just spoke about. So the results of that work from 2021 were kind of interesting, and just a little bit of history. So red, clear, blue CFA sets have often been uh, promoted in the industry because the clear channel um, has twice as much raw sensitivity as a green, and so often it will be sold on, hey, yeah, put a clear in there, and you get twice as much signal in your clear channel as you do for a green, and so you'll have a bit more sensitivity, and so it's really sold on that pre-CCM performance. What usually happens though is that as soon as you apply a CCM to it, because the clear channel is so much more sensitive than either the red or the blue. The red and the blue are generally the least sensitive, even in a RGB system. You end up having big disparities between what the clear can do and what the red and the blue can do. So as you use your CCM to twist to get back to RGB, you apply very big coefficients, and we'll get to that in a little bit. And you end up um, subtracting a signal that has a lot of noise in it, like the red or the blue, from the clear. So you end up correlating a lot of noise back into your signal. So if you look at on the left-hand side, pre-CCM luma SNR, then this is really what's used to sell RCB systems into imaging systems. Let's turn on a.
Robin, are those units in dB?
Yeah. I was going to turn on a laser pointer a second. Let's see if we can do that. So here we have luma SNR in decibels for the RGB, the RCB, the RYCY, and the RCG pre-CCM. And down this side, we have the demosaic, so no demosaic, bilinear demosaic, and a gradient edgeware demosaic, and then light level, 100 lux, 10 lux, 1 lux. And we can see pre-CCM, RCB clearly wins out, followed by RCG, and then RYCY and RGB. And we can see that there's a slight dependence on how sophisticated your demosaic is, but largely the results are very consistent. That for that there's more luma SNR because you have more signal in your clear, and that's why these two win out. As soon as you apply that twist for the CCM and you start subtracting those signals to get real color out of it, then pretty much everything reverses. So the RGB start and RYCY start to become the best, and then the RCB actually becomes the worst, post CCM luma SNR. And if we look at the RGB and then look at an average, and sorry, I should have said these are average for all the patches of the Macbeth color checker chart. So if we summarize those and we look at across all demosaic types and all patches, we see that with reference to the RGB system, post-CCM, RCB is losing anywhere between 3 and 1 decibel compared to RGB post-CCM. RYCY not quite so much. Anywhere, I've probably in the noises, anywhere between nothing and a 1 dB gain. And then RCG anywhere between, it's losing around about a decibel there. And this sort of pattern is repeated across the whole of the color checker chart. So this idea that you sell a system on the pre-CCM performance and you expect that performance to translate into post-CCM color corrected signals is a bit of a misnomer. It's misleading people. It's wrong usually. And another thing that we look at, so this really doesn't explain the color performance. So we also look at light spectra that we're really interested in. The color checker chart is useful for preliminary work, but it really doesn't explain what's happening in the application. So on the left-hand side, I have some spectra that we're interested in. So D65, of course, daylight. Then we have LED headlamps. We have green, yellow, and red LED traffic light spectra. And then we have green, yellow, and red incandescent spectra. And then on the right-hand side, we have the red, yellow, and white from warning signs. And then also we have the white and the yellow from lines as well. It's pretty important to be able to distinguish these because if you have a yellow line in the center of a road, it usually indicates you've got contraflow traffic, and that could be quite important not to go into the wrong lane. So what we can also do is calculate a color separation. So we calculate delta AB, which is really a Euclidean distance. But then we look at the noise in each of the A and B channel and divide by the noise that we find there. So this is a noise referred color separation. And the reason we do that is it's pretty much possible to correct or to twist any group of colors so that you get good separation. But if you're gaining a lot in either of a couple of axes, then really what you're doing is gaining up the noise at the same time, and so you really don't improve the separation. Because you're gaining up the noise at the same time as you're separating those colors. So that's why we do a noise referred delta AB to look at how far apart these colors actually are. And if we do that, take an account for which of the exposures that those lights or signs would fall into. So for the signs, they're really going to be, if we use twilight conditions, they're going to be in the long exposure of a HDR system. For the red and yellow lights, they're really going to be in the short exposure of a HDR system, so their exposure time is going to be much shorter in the microsecond sort of area, but they're going to be a lot brighter as well. So we expose, using this simulation, a 32 by 32 pixel patch. We white balance it, demosaic, color correct, and then convert to LAB. And then we can calculate this noise referred distance between two of the spectra that we want to look at the difference between. So like the red and the yellow LED for the traffic lights, for example, or the red and the yellow for the incandescent traffic lights, yellow and white lines, red and yellow signs, either mandatory or warnings, and then our yellow and white sign. And we find when we do this that post-CCM, once we've corrected for correct color, then the RGB system generally outperforms the RCB, which has been sold because it's more sensitive, the RYCY or the RCG. And so it's intuitive, it's unintuitive to a lot of people that even though this system, this RCB system, has this really sensitive clear channel, that if you're looking at color, then you can actually hurt yourself because the clear really carries no color information, and you're having to twist the signals that you're getting quite a bit to get real color out of it. Okay, so I promised to talk about some of the color correction matrices, and you'll see that we have each of the color correction matrices with the auto white balance or AWB terms included already in there. And if we look at the diagonal of the RGB, we can see that we're over 1 for each of those, so they're being gained up a little bit on the diagonal. But if we look at the diagonal terms for the RCB, the RYCY, and the RCG, we can see that all of them are most of them are higher than the RGB. So that's one issue that we have, that we're having to gain up the diagonal terms. So the center of the colors isn't very pure. And then also, if we look at the off-diagonal terms, a lot of them are much higher than the RGB coefficients as well. So really, before I go on, actually, the white point preserving least squares to generate the CCMs gave me a average delta E of about 3 across all of them. So it's a fairly fair way to generate a CCM. Maybe not the best, but a fair way to do it. So I'm pretty happy about that. But if we just sum the magnitudes of the gains that were applied, which is a very crude first order metric to look at how much we have to gain up each of the original colors and then subtract them, then we see that the overall gains that we're applying to the RGB are very much smaller than any of the other systems. And this really explains why we're getting better color separation for the RGB when we're looking at differences between colors than than any of the other channels as well. So it is predicting that RCG is the worst, and RCB is the worst. So RCB and RCG is the worst, and RGB and RYCY is going to be slightly better. So looking at the CCM terms, especially the diagonals and then the off diagonals, really gives us a little bit of insight about how much gain that we have to apply to these systems and how strong the twist is to correct the colors, and what we might get out of this. One of the interesting things, this RYCY, and this is what dropped out of the first word, this RYCY actually isn't as bad as it initially seems. And the only thing really stopping it from being a little bit better is it seems that we have to add a lot of red to balance the cyan, add a lot of red and yellow to balance the cyan to generate our green. So if there was some way that we could add less of the red channel and change this CFA channel so we could add less, then it might actually turn out to be a pretty good CFA set. It's already starting off in a better place than the RCB. So it kind of suggested, this first work kind of suggested, well, if we could change this channel, maybe we can get some of the sensitivity benefits and preserve some of the color separation at the same time. So it might be a good trade-off. And we can see some of the reason for that strong red and yellow, or the big gains in the red and the yellow counteracting that cyan. There's just really nothing down here to be able to balance this big bulge in the cyan. So really, there's nothing down here. So that's why we have to gain up a lot to be able to remove some of this to generate our green. So it seems that if we change the red to more of a magenta, then it would give us some power here, so we could take more of the magenta away and then better balance the three channels. So really what we're talking about doing here is balancing the three channels to make the CCM terms a little bit more uh, reasonable. And so if we do that and we add a magenta into this, which wasn't included in the original work, we actually get to this point where we improve the CCM terms quite a bit over the red, yellow, cyan. And also when we look at the sum of the gain magnitudes as well, we see it comes in second. It's pretty close to the RGB. So the MYCY actually turns out to be a pretty good candidate if we're looking for sensitivity, but we want to include a little bit of color. It actually has 20% more raw signal capture than RGB, than RCB. And it's got 107% for this CFA set than the RGB. So it could actually potentially give us one stop advantage if we do that. One thing to note, just at the back of your minds as I carry on, so RGB and MYCY seem to be coming out consistently at the top, and RCB and RCG consistently at the bottom in terms of the simulation. So that's really what we want to investigate, to see whether it could produce some decent results. So we do a spectral simulation, and this is pre-CCM luma SNR on the left-hand side for each of the patches of the color checker. And we see the usual pattern where pre-CCM RGB comes out the worst and RCB comes out the best, because that clear channel is very close to a luma channel. RCG also comes out to be very high. And then as soon as we apply a CCM to get some color out of this, the advantage of the clear channel is lost, and RGB comes out to be the best. RCB comes out to be the worst. And happily, it seems like what we predict for our MYCY seems to be true. It's coming out just behind the RGB. So at this point, we got a candidate CFA set, and we like it, and we want to start to investigate it, maybe with some sensor manufacturers. Sorry, I should have spoken about the color separation as well. So we're looking at close colors, the differences between close colors on the Macbeth color checker chart now, and looking at the separation between those as we go through the simulation. So we use patch pairs, and you can see we're looking at the close greens, or orange and burnt sienna, maybe I think it's called. And so we're looking at how far we can separate these colors. And again, for the spectral simulation, the RGB shows and MYYCY actually shows us that we have the best noise referred color separation, both pre and post CCM, which is nice. So it makes it, we think, a nice candidate for a CFA set for an automotive application. So we want to validate this. So now we want to try and persuade a sensor manufacturer to maybe give us a magenta, yellow, cyan, modern pixel, yeah, automotive pixel with our new CFA on it. And unfortunately, even just spinning one or two wafers will cost many tens of thousands of dollars, and so it's pretty difficult to persuade a sensor manufacturer just to spin you one or two wafers for to try this out. So we need another way of doing this, really, and this is where the spectral light source comes in. Usually light falls onto the sensor, filtered by the CFA, and that gives us our color in our pixel. And we can think of it a slightly different way. If we have white light falling onto the pixel, the filter is removing the other unwanted sources, other unwanted light at that pixel, and just leaving us with what we want. But that's exactly the same as having the light, instead of using white light, a colored light and no CFA. So if we could, instead of using a red filter, just color the light red and capture it using a monochrome pixel, then it would be exactly the same as having white light, having a red filter and capturing the red light. We wouldn't be able to spot the difference. So if we were to have some target CFA curves and we had a mono sensor, a monochrome sensor, if we divide the target CFA curves by the monochrome sensor, and then we multiply it by our desired illumination, that would give us a target light source spectra that would give us the equivalent of lighting with a white light, and then having the CFA curve up on the left hand side there. And so that's what we can do with this instrument from Image Engineering. It's a 20 channel programmable light source, and so we can generate these target illumination curves and program the light source, which has this closed loop. So it has a spectroradiometer in front of it, and so it's able to do a closed loop calibration to try to match whatever target spectrum that we want to reproduce. So for each of the CFAs that I generated in the beginning of this, using a monochrome sensor and knowing what its QE is, then I can generate these target spectra to simulate different CFA channels. So this is what we do. So we put something like a Macbeth color checker chart, and we illuminate it using our red, our green, our blue, cyan, magenta, and yellow, and clear sources. We get the following results. One of the reasons that we want to use the real sensor is we get real noise sources with the real pixel, and that gives us some really interesting behavior in low light. We can get the low light behavior nicely. We can get fixed pattern noise nicely. We can look at things like PRNU when we increase the light sources as well. So just looking immediately at the channels that we've generated using this this simulation technique. One thing to note is just how bright the clear is compared to, say, the red, or how dark the red is compared to the clear. That's really obvious. So this gives you a very good initial indication of what one of the problems with having a red channel is. It's very dark. The blue is pretty dark as well. From each of those 7 or 8 channels that we generate, we can select 3 of them and generate each of our pseudo CFAs now. So we can generate a RGB by taking the red, green, and the blue planes and putting them together. We can also flatten those, so then we can have a demosaic. This is important because there's twice as many green, so the SNR is weighted towards the green, so we want to make it fair. We can generate our MYCY, our RCB, RCG, and RYCY as well. A couple of things to notice when we do this. So first of all, just look at how neutral the MYCY is just straight away. These haven't been color corrected at all, and it looks incredibly neutral. I was really surprised. I wondered whether I'd taken the right image to put it in the presentation. It requires very gentle terms to color correct this, compared to, say, the RCB, which looks very green, or the RCG, which looks very green.
Pardon me, what was the illuminant illuminant color temperature or illuminant spectra that you were aiming for with that?
D65.
Okay.
I was aiming for a D65. Mostly because usually I'd like to go colder as well, if possible. So mostly at night it gets a little bit cooler in terms of color temperature. So I'd really like to push it actually to 9,000 if I could at some point, to see whether this holds up. Yeah, good question. I should mention that. The other thing to notice about this, the RYCY, it looks more neutral than, say, the RCB or the RCG, but it does have this pretty strong cyan cast, so it's going to require stronger terms than the MYCY, and then the RGB as well. It's pretty not as neutral as the MYCY, but it's pretty similar to the RYCY, but just in a different direction, in terms of color cast. So this is what we get, and my apologies to anyone that likes good image quality, because this is more of a simulation for engineering purposes. So what we do is we white balance and we color correct. Then we apply just a basic gamma correction, and then we scale the exposures as well, just to have a quick visual look to see whether what we're doing is reasonable. So these are not artistic quality renderings at all. But what we can see from this is, there's not huge differences between them. So our basic pipe of white balancing, applying a color correction, it seems to be working pretty well. There's nothing inherently unfair about it. The gamma correction is there just to add a bit of contrast so we can see what's going on, and the scaling is really between a black point and a white point, just to take out the effects of the exposure for the visual comparison, although it doesn't change the results at all that we calculate, because we calculate everything from the white balance color corrected point as well. So everything seems to be pretty fair in this sort of basic pipe. So one of the things that we want to look at straight away is whether our spectral simulation is matching our lighting simulation. So what we're looking for in the simulation is not exact matches between the numbers, but are the trends the same? So we have luma SNR in decibels pre-CCM, and this is each patch of the color Macbeth color checker. And we have the spectral simulation on the left and the lighting simulation on the right for each of the CFAs. And looking at just looking at the averages, the order looks to be around about the same. So we've got the RCB and the RCG, which are coming out the best in the pre-CCM because of those clear channels. The RGB coming out the worst, and the MYCY somewhere in the middle. So the order seems to be matching, which is really satisfying that we can do this. If we look at post-CCM luma SNR, again, spectral simulation on the left, lighting simulation on the right. Again, the trends seem to be matching. So we have this reversal that we were talking about before, because we have these strong color correction terms in the RCB. It comes out the worst, with the RGB coming out on top. And then happily, what we predicted would happen, our MYCY seems to be coming out just behind the RGB, and then RYCY and RCG somewhere in the middle as well. And again, it seems that the lighting simulation is matching the spectral simulation as well, which is pretty satisfying for that. So the lighting simulation seems
Hi.
Hello there. I thought I had a question. Chroma SNR, this was a little bit of a head scratcher, and still is a little bit of a head scratcher, actually, to be honest. So this is looking at the noise in the A and the B channels after conversion into the LAB. We get broadly the same trends, with the RGB coming out ahead, and the MYCY and the RCG coming out to be the worst, or around about the bottom. But we've got a couple of switching of orders, and what I've noticed is that in the spectral simulation, the SNRs for the neutrals are very low compared to the lighting simulation. And I've been trying to work out why that is, and I don't know whether it's due to some resolution issues in the spectrum, although I was simulating at least every 5 nanometers, or there's something going on here that I haven't worked out what it is. I've checked it a couple of times and get the same answer. So yeah, definitely that's where some of the difference lies in this. It might be a white point issue as well. I'm not sure whether the correct white point is being hit. Any suggestions? I'd be welcome. That would be welcome. Happily, post CCM, and this is why I think it might be a white point issue. The ordering seems to tidy up quite a bit, where it's clearly the post CCM chroma SNR is worst for the RCG, with the best performance coming out for the RGB and the MYCY. So I I think it's something to do with maybe the white point uh, used in the calculation, and it being a LED. So maybe I'm missing some energy somewhere. Color separation using the Macbeth color checker chart. Again, pre-CCM, the lighting simulation matches the spectral simulation pretty well, with RGB and MYCY coming out ahead of the RCG and RCB, which end up being the worst, happily. And then post CCM, we see pretty much the same order, with the RGB and the MYCY coming out ahead of the RCG and the RCB. So this is our theory is matching um, our sims and our lighting behavior, which is quite nice. So in summary, if we look at the pre-CCM metrics, luma SNR, chroma SNR, and color separation, it would tend to suggest that RCB is a good candidate. As soon as you start to color correct and uh, want to twist and gain up those signals to make real color out of them, RGB comes out ahead, with MYCY closely following. The lighting simulation matches the trends of the spectral simulation really well, and we still think that RGB is a really good candidate for automotive systems, with MYCY maybe being a close second candidate, and maybe we'll start investigating that a bit further with some hardware. The programmable light source is great. It really is a good tool to be able to investigate these sorts of things. One of the things I didn't say is it can support other algorithm development as well, because you have a full plane for each of the red, green, blue, cyan, magenta, yellow, and clear. You can create 4x4 or even n by n Bayer patterns. So you can look at what a 2x2 or a 4x4 or even a 6x6 cell could give you in different orders as well. So looking at better performance for demosaic and different CFA outlets as well. The programmable light source also helps you to get real noise performance. So what you can do is put good quality neutral density filters in front of your camera and get down to very low light levels. So believe it or not, I'm being asked for what the performance looks like at 1 lux nowadays, with 0.1 lux also being used as a reference point, just to see what it looks like. When I started out working with digital imaging, 50 lux was considered low light, and now really it's not until you get below 5 and 10 lux that people are starting to think about it being really low light. The lighting simulations match the trends of the spectral simulations really well. So that was really interesting to see. MYCY seems to be a viable alternative to RCB. If I had a choice between the two, I'd certainly look at MYCY. Better balance between the channels lead to smaller white balance terms and smaller twists on the CCM coefficients. And of course, that gives us more control of the noise amplification. I won't read out the orders of everything else. I think I've belabored that point quite a bit. But thank you very much for your attention. I'd be very happy to answer any questions that folks have.
Very good. Thank you.
Thank you very much, Robin.
Oh, you're welcome. I enjoy it.
Questions from people online?
Yes, this is Sai. Hey, Robin.
Hey, Sai.
We worked in the past, and I 100% agree with you that MYYCY is actually a very, very viable alternative to RCB. And MYYCY, we have kind of tested it in slightly a different way for some advanced project in the place that I previously worked for. We found out that it's actually giving us good options for sensitivity and better SNR and better contrast for object detection. So I can't agree with you more on your presentation.
Good to hear.
I'm very happy, very, very happy that the world is going in the way that we are planning to go.
Great to hear. Glad that someone's tested it out.
We have a question from Charles. Charles, would you like to unmute?
Yeah, I think I am unmuted. Can you hear me?
Yes, very good.
Yeah, good. So I have sort of I have a question that I posted in the chat, and it's already been answered by one of the participants. But for you, and not delivered by chat, delivered in person, I've got two terminology issues. One major, one minor. So
Okay.
the first, I realized looking at the participant list, there's probably 3 or 4 people who've heard me on this soapbox before. But I basically object to the term CCM because according to my philosophy, the so-called red, so-called green, so-called blue signals from a sensor, which I think are more accurately called shortwave, medium wave, long wave, are, in my opinion, 3 signals having different spectral signatures, but they're not colors yet. And they're only colors when you impose a certain assumption about illumination and overlap and spectral content of the scene in usually in a matrix. It's not always a matrix. In some high-end cameras, it's a little different today. So then put very briefly, my philosophical position causes me to call this a color formation matrix, not a color correction matrix. And the reason I kind of climb onto this soapbox is I think it's a pedagogical issue. I think it helps the industry as a whole to understand that nobody can expect a camera to be hooked up to sRGB and deliver meaningful colors.
Yeah, I hadn't heard that before from you, Charles. I wonder how I missed it. But I do agree with you. Absolutely. And some of the other work that I haven't presented here really is looking more at the separation between signals. And I have a smaller but somewhat related soapbox myself, which is that we should be talking about signal separation rather than color separation, and thinking about especially automotive systems as looking at we should be treating them much more as measurement devices rather than cameras, and talking about signals and signal separations and information content, and really reducing it to almost analog measurement devices in some sense.
Oh, 100%. I like that soapbox a lot. I might start using that line and credit you, of course. And that exact idea, treating a camera as a data acquisition device, there's a current, pretty big and interesting discussion at the high end of motion picture cameras about exactly that.
Oh,
And
really?
there's certain proponents there, in particular, a very accomplished ASC cinematographer called Steve Yedlin, who makes exactly that claim. He believes the most productive way to capture a movie is to treat the camera as what he calls a data acquisition device.
Mhm.
And your, signal separation idea folds perfectly into that. Then my other little terminology point is about luma. And I would always prefer to use the word luminance, or if you don't want to impose a certain spectral distribution, the Y-bar function, then you could just call it tristimulus.
Mhm.
But that's appropriate in radiometric space, where as soon as you do something like a square root or a log or some gamma correction, then it's closer to what a video person would call luma. And
Yeah, fair point.
yeah, good. Thanks for the talk. Really interesting, really good.
Yeah,
And thanks for the comment.
I have a question. Can you hear me?
Yeah.
Okay. Automotive image sensors. Like a big thing is you want to be able to look out of a tunnel when you're coming through it. So you both have dark regions and bright regions, and they don't want to have to use another camera imaging system because they have to spend like $500,000 when they train their programs to run it. With all this, that said, if you look at the human eye, our rods and our cones form really two cameras that happen to be in our eye. Our rods have linear response and they saturate when we go outside. Our cones are effectively a log response and they're the HDR part of our imager. I mean, our cones are, so they give you the color. Have you looked at looking basically at two imagers side by side, one being like a larger pixel monochrome for doing the night, and then you have a second camera next to it that's basically an HDR imager for the color. And then what you do at night is then you average the color in low light situations and superimpose it on the luminance channel that you get from the monochrome.
Yeah, it's a good point, and I think it's becoming more important. The short answer is yes.
Okay.
We have an incredible dynamic range to deal with in automotive imaging. I've estimated it as, if you have someone with dark clothing at night, only illuminated with a headlamp at the edge of its distance, maybe one lux, and then you go all the way through to something like the sun, and I'll justify that in a second. You've got something like 29 bits, something like that,
Yeah,
maximum
exactly.
scene dynamic range. And we try to do our best. It's a little bit less if you just look at brake lights and things like that. But capturing as big a dynamic range as you can helps you with flare around the sun. So if you have traffic lights behind the sun, it actually helps quite a bit to reduce the size of that flare.
Exactly. Yeah.
Yeah. But at the same time, trying to get the low light response good enough that you can meet the requirements of something like FMVS S127 is just super difficult. So one of the
Yeah.
things that I haven't published yet is looking at combining something like a 4.2 micron clear channel sensor with what's currently used for the forward-looking cameras, which is we seem to have settled on the 8.4 megapixel 2.1 micron as a node. If you look at the difference between a green 2.1 micron pixel and a clear 4.2 micron pixel, you've got something like 3 stops difference between the sensitivity of those two straight away, which is great. But then if you can just open up the lens slightly as well, which your 4.2 micron pixel will allow you, you could possibly increase that to a 4-stop difference. So you could have something like the big clear pixel filling in shadow regions for you, and still using your 8 megapixel color sensor to reach everything else.
Yeah, well, this gets into this whole thing about automotive, because you're basically trying to process the image and pull the data out. And the way the human eye works is basically we're using the rod channel. And if you look at the eye, with the rods actually have 2 layers of neurons in the retina before the data is even sent back to the brain. And there's a lot of processing that's going on at the retina level, because there's really 100 million rods and only 1 million optic fibers coming back, neuron fibers coming back. So there's obviously a lot of signal averaging going on to get you the low noise response. The color is different, but then it becomes a question is how are you processing that data in the brain, which is getting back to what you're saying. This is a data acquisition device, but then you have to process the data post to sort out the imaging stuff, which is what I think is actually the most interesting part, is how do you start drawing the block diagrams now to sort through all the color channels. And one thing, this is a totally separate thing. I was talking with somebody a while ago. I'm an image sensor guy. I'm not a color scientist guy, so I'm getting out of my league here. But if you look at the LGN, the lateral geniculus nuclei before the data gets passed to the cortex, there are effectively 6 layers of neurons there. 2 of them look at the rods, and 4 of them are for color. I am convinced we are doing the pixels in our eye, the red, green, blue, are actually doing a CMY transformation at that point before the data is passed back to the visual cortex. I haven't been able to find a cross section on cats and dogs that have 2-color vision, because I'm really curious what the neuron structure looks like in the LGN. The reason I'm bringing this up is because if you look at the human eye, the green and the red response is really they're horrendously close. And so what the human eye is doing compared to what these cameras are doing are very different, because the blue, green, and red channels, the CFAs that we use, the color filter arrays, have been tuned to actually give you the minimal amount of color noise, to separate the colors. But the human eye doesn't work that way at all. So that's something that I've always been very interested in. I don't know the answer, but the human eye is very different from what the image sensors do in terms of spectral response. Sorry, yeah. I'm getting off tack. Yeah.
No, I think it's relevant. I'm optimistic about the future of image sensors. There's a lot of recently, folks have worked out how to layer data processing just behind the pixels, which is quite nice. And I hope people look towards some biologically inspired processing, like you're suggesting, to do some of this processing prior to sending the data back. One of the big problems that we have at the moment is that we find it difficult to consume all of the data that's generated for us. The latest ISP from NVIDIA that's built onto the SoC will process something like 3.6 gigapixels per second. And we need to do that so we can keep the latency down as much as possible. But if you start multiplying 30 frames a second by 8 megapixels or by three megapixels around the edge, you hit 3.6 gigapixels a second very, very quickly. And that's always an issue.
Yeah. Oh, well, I appreciate the talk. I could talk for hours about this, but I'll stop here. So
Yeah, we're lucky to work in this field, huh?
Robin, I'm Wayne Prentice, and I really appreciate your talk, and I'm really happy about the subject.
Thank you, Wayne.
I work for, I consult with a company who's an NVIDIA support group. I guess, you know, they people buy NVIDIA chips and they're not big enough to get NVIDIA. So they get one of these companies to support them. And I support that one of those companies. And they usually come and say, we've picked a sensor, we've picked a lens, and we've picked a processor. Now we'd like you to meet these key performance index, you know, values. And of course, you've made all the decisions. There's really not much left to do.
Right.
I've done the same analysis at a much simpler level just to make the proof that what you did, that at the time it was really the clear pixels versus the RGB. And it's easy to prove that the clear pixel is not your best friend, mostly because the matrixing and the channel disparity. I was going to say, I think I know the answer, but for the numbers that you reported, those also include the white balance gains. In addition, when you say post-CCM, it's post-white balance CCM, so the channel gains are included as part of the noise amplification. Is that right?
Yes, and I did that on purpose actually, because I did have a version of these slides where I separated out the white balance gains and the I'm going to start calling it the CFM twist.
Thank you very much.
So I separated out the white balance terms and the CFM twist, and it was very difficult for people to quickly eyeball the total gain for the channels. So that's why I concatenated them and put them in together.
Okay, very good. That's what I thought it was in there, but I thought I just asked the question. So that also says that you know the as you showed the magenta flavor really worked well, in part because the channel gains were already balanced for the illuminant you tested with, which meant the only penalty was the amplification from the color correction terms.
Right. It's a lot gentler. It's a lot better for us. And of course, one of the things that I maybe I should have said, I often thought it was obvious, is you know, whether you add signals together or whether you subtract signals, then you're adding the noise by quadrature. So you can't win either way, you know.
Right.
So getting those magnitudes of getting the total magnitude of the gains down, which is why I use the sum of the gain magnitudes.
Mhm.
Get that total down is really
Right.
what you want to do. If you could get it down to 3, you know, then it would be perfect.
Right.
And no, 1, and actually
Yeah,
1.
yeah,
If you could
yeah,
get it down to
that'd be
1, it would be
right.
perfect.
That would be the perfect matrix.
Yeah.
So you just, I think you said these are all done at D65. If you had halogen headlights, for example, that might throw, would that tilt the scales to a different flavor, or the annoying blue headlights which exist today, or the annoying sodium vapor lights or mercury vapor lights or some of those other nasty light sources out there? I'm wondering.
Yeah, it would be an interesting exercise to do to see how much it swings the other way when you add in that yellow content from the halogen, or the sodium vapor. I'm not sure we can do anything about. Hopefully that's going to disappear and never come
Right.
back.
Unfortunately, most places are going to LED lights, which are a little friendlier, but no better defined. Right.
Right. Absolutely.
One more comment I wanted to make. In your slide 8, you talked about using the delta AB noise for color discrimination. I'm curious your thoughts on this. I'm in general, this is a broader topic than this. We're talking about this in the context of not not human vision, not humans looking at these pictures and trying to make discrimination tasks. What's a stop sign? What's a yellow line? Because we don't need the human, right? This is all in the context of a computer vision system. And in a computer vision system, you know, delta AB is meaningless, right? The
Yes.
computer vision system will pick whatever basis
Right.
colors, I don't, for lack of a better, basis channels it needs in order to form a discriminate, you know, which provides the best discrimination task. And one thing I've been trying to, everybody I guess has got their horse to ride, right? Right. Mine is, we can learn from human perception, but trying to use the ideal human perception system is therefore the ideal computer vision system. I think is not necessarily true. And when we try to optimize systems, we know it works great because we have the best delta E, lowest delta E star, and best chroma noise, right? They may be predictors of that, but I'm not convinced that they are necessarily that.
I would agree to a certain extent. So the first thing I would say is signs and lighting designed for humans is going to be around for a long time because driving is an inherently visual process. But optimizing systems solely based on that is probably the wrong thing because we're better than that. We can add in radar, lidar, and all sorts of other things as well to enhance it. So I think you're right in that sense. I actually this is going to be shooting myself in the foot somewhat, but a plug at the same time. I actually don't like this metric that I've got here. It's essentially a Euclidean distance, and Euclidean distances are variant under linear transformations. They're not invariant under linear transformation, and so
And you're in root space just to get to AB.
right, and one of the problems. So you can imagine if we even didn't go into LAB, you do a 3x3 twist, and if you had a certain separation between signals in your 3D space before, and then you give it a twist to a new space, your Euclidean distance can go up as well as down, depending on the dot product between the major axis and the minor axis that you're stretching, and that's a real problem because say you happen to be aligned in such a way that your Euclidean distance goes up, then your color separation metric would go up. And so it would suggest that you have more information in your twisted output than you do in your original. And that can't be true.
Oh, you can create information out of the blue. It's done all the time.
So this is and now to the plug. So I don't think this metric is what we want to use for color separation in the long term. I think putting human vision aside for a second, I think using something like Mallahan-Nobis distance, which takes care of covariance and is invariant to linear transformations, is actually the way that we want to go. And the nice thing about that is if you go from, say, a multispectral space into a reduced color space, or reduced dimension space, the Mallahan-Nobis distance can only stay the same or go down. And so it seems like a really good candidate to calculate, and I'm going to use the term signal separations in multiple dimensions from one between transformations that'll remain consistent. So I've done some research on it. It looks really promising, and I will publish that at Electronic Imaging, which is March 1st to the 5th, if you haven't already booked your ticket.
Very good. Thank you. Henry had a hand raised. Would you like to make a comment, Henry?
Yeah, sure. I lost my question here, but it was kind of around the visible centric sort of nature of this. And I think my question was like, does ultimately transforming to RGB kind of predetermine that RGB sensors are going to perform better? And then kind of the second part of the question is like, is looking at more at near infrared future work here, or has that just kind of been tossed out because it's not part of the human visual spectrum? And I have a little bit of a bias here because I have a tendency to wear dark T-shirts, which I think is increasing my likelihood of getting run over. I noticed that dark fabrics seem to actually be quite reflective at night, under near infrared. So that makes me think that maybe there's some value in having that extra near infrared channel for detection purposes. That's my rambling question.
Right. Okay. So, two parts. So, moving to something like Mallahan-Nobis distance for signal separation, I'm actually trying to include the opportunity to have multi-channel systems. So, like RGB-IR, or things that are non-visible as well. And there's other reasons to do that as well. When you start adding spatial aspects into this, it's good to do that for detection theory and things like that. In terms of whether RGB turns out to be the best because we're transforming into an RGB, it's possible. It's very possible. If you had filters that were aligned with each of the axes of your intended dimension straight away, then of course your CFM terms, I'm trying to keep on using that for Charles, your CFM terms would align perfectly and be very low. So I think it's answered in the matrices, isn't it? That if your original capture dimensions match your final dimensions really well in terms of alignment, then of course you're going to get better performance. I think.
Yeah, just to build on that, yeah, I think making the assumption that sRGB is this magical color space for which all image science or each computer imaging should occur in is probably not correct. And the network's going to have its own native color space to create its own discrimination tasks, which no doubt does some color mixing inside of it, and ultimately ends up with some colors unknown to us. And so it may very well be that C, clear red and blue, may be the ideal one, right? Because all it really needs is structure. It doesn't really care about color, and every so often it cares a little bit about some discrimination, but not much. It's mostly entirely structure, and not color discrimination that in the end serves that particular computer vision task.
Yeah, it's very difficult to know what it's using at these very deep levels in the network, because it may well be influenced by context as well. So it's not just that you got a red light, it's where the red light is in the image and what's next to it and things like that. It's really difficult to understand the relative importance of pure color compared to structure.
I mean, the comment earlier about our the color discrimination we have in red and green, you know, we have that because we need to find ripe berries, you know, and that helped us survive. And so the ability to detect ripe berries probably is a different skill set than what it's necessary to survive driving a vehicle.
Yep. Yeah, I couldn't agree more.
Excellent talk. Thank you very much.
Yes, I really appreciate it.
Yeah, it was good, Robin. Thank you. Cheers.
Thank you so much. I appreciate it.